Welcome to 27th lecture in the open course on diffusion in multi-component solids. In this lecture, we will go over one more boundary value problem with periodic boundary conditions. In this problem, initial concentration profile is represented by a square wave type of pattern, and we will solve the diffusion equation by separation of variables. So, last class we talked about homogenization problem. We solved the diffusion equation for periodic boundary condition pertaining to the homogenization. The initial condition there, the concentration profile initially in there was a sinusoidal type of wave. We just had one equation for C at x and t equal to 0. Today, we will solve another problem in which we will solve the diffusion equation for periodic boundary condition. Here the initial profile is little different. We will deal with a square wave type of profile to begin with. So, the problem is a steel of eutectoid composition was found to have the lamellar spacing of perlite to be 2L. So, the period here is 2L. The average thickness of each cementite layer is 2H. This steel was heated to 850 degree centigrade for austenitization, which proceeds by diffusion of carbon atoms from cementite into austenite. Assuming that the transformation of ferrite to austenite does not take much time, derive the equation for concentration profile of carbon developed in a perlite colony during the austenitization. You can assume square wave type initial profile in perlite with 0% carbon in ferrite before the dissolution starts. Assume no discontinuity of concentration at the interface. So, we have a eutectoid steel here. The eutectoid microstructure basically is composed of alternate layers of ferrite and cementite, which is shown here in this figure. So, in this figure, the hatched area is a cementite layer and the other layer is the ferrite layer. This is the profile to start with. The concentration of carbon in ferrite is 0 and the concentration in the cementite, let us denote it as a C epsilon. Now, we are dealing with a perlite spacing of 2L. So, the period here is 2L and each cementite layer has a thickness of 2H. So, if we consider our x equal to 0 at the center of any of the cementite layer, then the two edges of this cementite layer would be x equal to minus h and x equal to plus h, and since the period is 2L, the center of the two adjacent ferrite layer will be x equal to minus L and x equal to plus L. Now, this problem is little bit simplified here, because this is actually a multi-phase diffusion problem. We are having cementite and ferrite, two different phases. Obviously, it is given that the ferrite quickly transforms to austenite as soon as the steel is heated to the 850 degree centigrade temperature. So, we are dealing with austenite and cementite, and since the equilibrium concentrations of cementite and austenite are different, we expect that there should be a discontinuity at the interface between cementite and austenite. But for the sake of solving this problem, we are ignoring this discontinuity. We are treating the concentration profile as a continuous profile at any time t greater than 0. Obviously, at t equal to 0, it is a square wave type of profile. So, we are treating it just like a single phase diffusion condition. Also, we are assuming that diffusivity is constant. So, essentially we are solving the diffusion equation, which can be written as dou C by dou T equal to D times dou 2C by dou x2. The initial condition here is at T equal to 0, we know the concentration in any cementite layer is C epsilon, and in any ferrite which has been quickly transformed to austenite is 0 to start with. So, C at x and T equal to 0 is equal to 0 between minus L and minus H. So, minus L less than x less than minus H, it is equal to C epsilon between minus H and plus H, minus H less than x less than plus H, and again it is 0 between plus H and plus L, equal to 0 for H less than x less than L. And the boundary conditions are the no flow condition, which means the concentration gradients are 0 at the boundaries and at the middle of the profile. So, if you consider middle of any layer, ferrite or cementite, the concentration gradient is basically 0. So, dou C by dou x is equal to 0. So, dou C by dou x at x equal to 0 is 0, and also the gradient at x equal to minus L and plus L are 0, and so on. And this is a periodic boundary condition. So, we have a periodic profile here. We need to solve this equation. For periodic boundary condition, we can use separation of variable. So, let us assume that C of x and t can be expressed as an explicit function of x and t. So, we express it as a product of a function of x and t. Capital X is a function only of small x, that is the distance coordinate, and capital T is a function only of small t, that is time. So, with this, dou C by dou t becomes, since x is only function of x, we have dou t by dou t, and dou since t is only function of time t. So, we can replace this partial derivative with ordinary derivative. So, we can write x times t dot. Similarly, the second partial of C with respect to x becomes t times d2x by dx2. Again, x is only function of distance coordinate x. So, we can replace this dou 2x by dou x2 with d2x by dx2, and this we write as t times x double prime. So, if we substitute in the diffusion equation here, we get x t dot is equal to d times t x double prime, which yields, if we rearrange, t dot over dt equal to 1 over x times x double prime. Now, if you look at this equation, the left hand side of this equation is only function of time t, and the right hand side is only function of distance coordinate x, and x and t both are independent. So, this equality would be true only if both the sides are equal to a constant. Let us denote that constant as minus lambda square. So, we get two individual differential equations, one for t and one for x. We can write t dot plus lambda square dt equal to 0 and x double prime plus lambda square x equal to 0. So, the solutions for t and x are, as t is equal to t0 exponential minus lambda square dt, and for x the solution can be a prime cos lambda x plus b prime sin lambda x. Now, this will be true for large number of values of lambda. and the linear combination of the solutions will also be a solution. So, we can express the function c of x t in the form of a series as c of x t is equal to summation of a n cos lambda n x plus b n sin lambda n x times exponential minus lambda n square dt, n here varies from 1 to infinity, plus a 0. A 0 is the value of a n at lambda n equal to 0. Now, we need to find out these constants. So, we use our initial and boundary conditions for this. So, first we will use the boundary condition. For boundary condition, we need to evaluate the derivative. So, dou c by dou x would be dou a 0 by dou x is 0, summation n equal to 1 to infinity, dou by dou x of cos lambda n x is minus lambda n sin lambda n x. So, this would be minus a n lambda n sin lambda n x plus b n lambda n cos lambda n x, and the exponential term is independent of x. So, it will be as it is exponential minus lambda n square dt. Now, at x equal to 0, this derivative is 0, and if we substitute at x equal to 0 in the right hand side here, sin 0 is 0 and cos 0 is 1. So, we get sigma n equal to 1 to infinity b n lambda n exponential minus lambda n square dt. Now, for this to be true, we should have either b n equal to 0 or lambda n equal to 0. But if we put lambda n equal to 0, then we get a trivial solution independent of time here. So, lambda n cannot be 0, and so all b n's have to be 0. Now, we have dou c by dou x at x equal to L, which is also 0. So, if we substitute for x equal to L in the right hand side here, we know b n we have already got as 0, should be equal to n equal to 1 to infinity minus a n lambda n sin lambda n L times exponential minus lambda n square dt. Now, if this has to be 0, then either n is 0 or lambda n is 0, or this term sin lambda n L is 0. Now, sin lambda n L is 0 when lambda n L is an integer multiple of pi, that is when lambda n equal to n pi by L, where n is an integer. Obviously, a n and lambda n cannot be 0, otherwise we will get a trivial solution. So, this will yield a trivial solution. So, we have lambda n is equal to n pi over L, and so we get c of x t is equal to a 0 plus sigma n equal to 1 to infinity a n cos of n pi x by L. We substitute for lambda n here, b n is 0 times exponential, substitute for lambda n square minus n square pi square by L square dt. So, now we need to find out the values of a 0 and a n. In order to get the values of this, we will use the properties of integral of periodic functions. sin n pi x by L cos n pi x by L and their products. So, let us quickly refresh these properties. So, we know integral minus L to L sin n pi x by L dx is equal to 0, integral minus L to L cos n pi x by L dx is equal to 0, then integral minus L to L sin n pi x by L sin m pi x by L dx is equal to 0 if m is not equal to n, and this integral is equal to L if m is equal to n. Now, both m and n here are integers. Similarly, integral minus L to L cos n pi x by L times cos m pi x by L dx equal to 0 if m is not equal to n, and this is equal to L if m is equal to n. So, to make use of this, let us first denote this equation as equation 1. Now, we have the equation for C of x t, which is given by equation 1. Now, we will use the initial condition C of x 0 would be a 0 plus sigma n equal to 1 to infinity a n cos n pi x by L, and exponential 0 is 1. So, let us call this equation 2. Now, to make use of this properties of the integrals, let us first take the integral on both sides between minus L and L of equation 2. So, we get integral minus L to L C of x 0 dx should be equal to a 0 integral minus L to L dx plus sigma n equal to 1 to infinity, a n's are constant. So, we can take it outside the integrals, integral minus L to L cos of n pi x by L dx, and n is an integer here. So, using this second integral property, we see this integral will be 0, and C of x 0 between minus L to L. We know between minus h to minus L, between minus h and minus L, and between h and L, C of x 0 is 0, and between minus h to h, C of x 0 is C epsilon. So, we need this integral between minus h to h, at which the value of C of x 0 is C epsilon, should be equal to a 0 times integral minus L to L, this should be L, integral minus L to L dx should be 2L, and this is 0, and C epsilon is a constant. So, we get a 0 is equal to C epsilon times h by L, because this integral on the left hand side here is nothing but C epsilon times 2h. So, you got the value of a 0. To get the value of now a n, let us multiply both sides of equation 2 by cos m pi x by L, where m is an integer, and then integrate between minus L to L. So, we get integral minus L to L C of x 0 cos of m pi x by L dx is equal to a 0 integral minus L to L cos of m pi x by L dx plus sigma n equal to 1 to infinity a n integral minus L to L cos of n pi x by L times cos of m pi x by L dx. Now, straight away the first integral on the right hand side is 0. The second integral, we know this is 0 for all values of m which is not equal to n, and this is equal to L when m is equal to n. So, in this summation all other terms will vanish except for m equal to n. So, we can write integral minus L to L c of x 0 cos of n pi x by L, because m is equal to n. So, we will substitute m with n here, is equal to a n times L, because the value of this integral when m is equal to n is L. Again c of x 0 is 0 for the limits minus L to minus h and for h to L, and between minus h to h this value of c of x 0 is c epsilon. So, we get c epsilon integral minus h to h cos of n pi x by L dx is equal to n times L. So, if we evaluate this integral, we get c epsilon L over n pi sin of n pi x by L from minus h to h should be equal to n over L. So, we get c epsilon over pi into 1 over n into sine of n pi h by L minus sine of minus n pi h by L should be equal to n into L. So, this L and this L will get cancelled, and sine of minus n pi h by L is minus sine of n pi h by L. So, we get 2 c epsilon over pi times 1 by n into sine of n pi h by L should be equal to a n. So, we now got the value of a n 2. So, if we substitute for a n and a 0, we get the solution for c of x t in the form of a series. C of x t is equal to a 0 is c epsilon times h by L plus 2 c epsilon over pi summation over n equal to 1 to infinity of 1 by n sine of n pi h by L into cos of n pi x by L times exponential minus n square pi square by L square times dt. So, this is the solution that we have obtained. Okay. So, this is how we can work with the periodic boundary conditions and solve the diffusion equation using first separation of variable and then using the series expansion. Again, we dealt here with the austenitization problem, which actually is a multi-phase problem. The concentration profile will be little bit different because of the discontinuity at the interface at all times. As long as the interface is there between two phases, there should be a discontinuity in the concentration profile. We will see the more accurate type of profiles later when we study the multi-phase diffusion, but in order to understand how we solve the periodic boundary condition problem, I just oversimplified it and just used it as a single phase diffusion problem. Okay. So, this gives us a good flavor of solving the diffusion equation for periodic boundary conditions. So, we will stop here. Thank you.